stock price prediction project. This project focuses on accurately predicting Microsoft's weekly stock returns through historical data analysis and machine learning techniques. We'll be going through introduction of the problem, then the problem statement, then data preparation, then model selection and the evaluation, and at last we'll discuss the results. So our project aims to predict weekly returns on Microsoft stock by analyzing both historical data and data from correlated assets. By combining regression and time series models, we aim to find the most effective approach for short-term stock prediction. Stock movement is influenced by multiple factors beyond the company itself, such as currency fluctuations and competitor performance. Accurate predictions can aid in making better investment decisions and minimizing risk. The objective is to forecast Microsoft's weekly stock return using historical price data and returns from correlated assets like competitor stocks and currency pairs. Our main variable of interest is Y, is the weekly stock return of Microsoft stock, and our independent variables X, which include competitor stocks like IBM and relevant currency pairs and indices such as S&P 500. This multiple dimensional data aims to provide a broader understanding of Microsoft stock performance. For data preparation, we have extracted information from sources like Panda Data Reader for stocks, currencies, and indices. We used logarithmic differences to calculate returns, normalizing price variations to reduce the effect of extreme values. The weekly returns are approximated using 5-day period to align with trading cycles. Key features included lagged returns from Microsoft and correlated assets to build a robust predictive model. To predict Microsoft stock return, we used various regression models such as linear lasso, elasticnet, and some time series models like ARIMA LSTM. Linear regression models generally perform well, but ARIMA model outperformed others on the test set with a configuration of 201. The selection of ARIMA highlights its strength in capturing sequential dependencies effectively in time series data. In terms of results, the ARIMA model was the most successful, achieving a strong balance between low bias and prediction accuracy. Linear models also performed well, confirming the presence of strong relationships in our data. As next step, additional indicators like PE ratio or trading volume could be incorporated to enhance its predictive power. Let's move on to the coding part now. We start by loading the necessary packages or the Python packages for our project. Then we load the data, namely Microsoft, IBM, Google, DEX JPS, and DEX US UK. This is nothing but the Japanese yen versus the US dollar and US dollar versus the Great Britain pound, and index tickers such as S&P 500, Dow Jones Industrial Average, and VIX CLS. We have also included we have taken these tickers from basically Yahoo and Fred. Yahoo for the stock data, currency data is from Fred, and index data is also from Fred. So next we need a series to predict. We choose to predict using weekly returns. We approximate this by using 5 business days as the return period. We now define our Y series and our X series. Y series being our Microsoft future returns, and X series is a list below here. And as you can see, it is Google's. For everything of the above mentioned tickers, we have taken only 5 business days except for Microsoft. For Microsoft, we need a lagging based return period to just find the correlation and like what is the basic trend in the stock, since we're going to predict it. So we have taken 5, 15, 30, and 60 business days returns. We remove the Microsoft past returns when we use the time series model, so we are this is just for that. Exploratory data analysis. So at first we do the descriptive statistics, which is nothing but we are doing dataset describe here, and this is displaying just the 5 columns of the dataset, 5 rows, first 5. Then we visualize the data to get some insights, starting with just a histogram pie plot. This is the yen versus the US dollar versus GBP, Dow Jones Industrial Average, Google, IBM, Microsoft 12 days, Microsoft 6 days, Microsoft 3 days, Microsoft 1 day, and S&P 500 VIX CLS. So this is just the movement between them, the price movement. Then we plot the density plot for the above price movement. As you can clearly see, the VIX index has the highest or the largest variance compared to other distributions. This one. In order to get the interdependence of the data, we look at the scatter plot and the correlation matrix. In the correlation matrix, you can clearly see there is a correlation or kind of higher correlation values between the lagged 5 days, 15 days, 30 days and 60 days of the Microsoft return. Naturally, they show higher correlation between them. We can just use the scatter plot to confirm it clearly. In the scatter plot, you can also see there is a linear relationship between 15 days, 30 days and 60 days of Microsoft stock returns. So we can say they are highly correlated. Then we do some time series analysis. Here mainly we look at the seasonal decomposition of our time series, which is this one. And we can, by this we can actually tell Microsoft is generally moving upwards. So we can put this as a bias in our model, that Microsoft is generally trending upwards. Then let's move on to data preparation and feature selection. Here we use sklearn select best feature function to get sense of feature importance, and these are the scores after that. And we can clearly see IBM has the most important feature and VIX being the least important. Then let's move on to evaluating our algorithms and models. As mentioned before, we are going to use few models and we'll check which one works the best. Here we have, here we are just training, we are doing the training and test split, and these are the test options such as 10 folds and 7 seed. We're assigning it, and for scoring we're using to avoid confusion in scoring and to allow comparison with other models, we invert the final scores. So we are using neg mean squared error as our scoring function. Then we compare the models and algorithms. First we are using here is the machine learning model. The machine learning models like regression and tree regression algorithms, linear regression, lasso, elastic net, k neighbors regressor, decision tree regressor, SVR. For neural network algorithms we've used MLP regressor, and the ensemble models are ADA boost regressor, gradient boosting regressor, random forest regressor, extra trees regressor. Once we have selected all the models, we run the k-fold analysis. Next we run the model on the entire training and test data set, which is being done here. Then let's plot the k-fold results and we'll find it. Just the box plot to initially see. We can see linear regression and regularized regression including lasso and elastic net seem to be doing a good job. And then let's find out the training and test error and compare them. Here, as you can see, looking at training and test error, we still see a better performance of linear models. Some of the algorithms such as the decision tree regressor overfit on the training data and produce very high error on the test set, and these models should be avoided. Ensemble models such as gradient boosting regressor and random forest regressor have low bias but high variance. We also see that the artificial neural network algorithm shows higher errors both in training and test set, which is perhaps due to linear relationship of the variables not captured accurately by ANN, or maybe insufficient training or improper hyperparameters. Let's move on to time series based models such as ARIMA and LSTM. Let's focus on dataset for ARIMA models by having only the correlated variables as exogenous variables. Then again we are putting the tickers here for both test and train. We are training the ARIMA and checking the error rate. Error rate is fairly low for ARIMA model. Then let's move on to the LSTM model. mm, we are using segment length as 2 for LSTM model here, and here we're training the LSTM model, and we'll find out, and then in the end we're plotting the train test error. As you can see, the training error is fairly being lower compared to other models, and we'll append it to the previous results and plot it again to check what is the error rate compared to other models. Looking at the chart above, we can clearly say ARIMA model is comparable to linear regression such as lasso regression, elastic net. This can primarily be due to strong linear relationships as discussed before. The LSTM model performs decently, however ARIMA model outperforms the LSTM model in the test set, hence we select ARIMA model for our model tuning. Let's move on to the model tuning and grid search part. So as shown above, the ARIMA model has a default order of 100. We'll perform grid search with different combinations, and we'll find out the best possible order for our ARIMA model. Here we are doing the grid search, and we get the result like ARIMA model performs the best with the parameters 2, 0 and 1 with a MSE of 0.0008481. So we are finalizing this ARIMA model, and once again we'll print the mean squared error, which is the lowest by far. So we'll save this model for later use by the Python package called pickle. We are saving it here, and let's conclude this. So we can tell कि linear regression models, regularized regression like lasso, elastic net, along with the time series models such as ARIMA are promising modeling approaches for asset price prediction. These models can enable financial practitioners to model time dependencies with a very flexible approach. The overall approach presented in this case study may help us encountering overfitting and underfitting, which are some key challenges in prediction problem in finance. We should also note that we can use better set of indicators such as P/E ratio, trading volume, technical indicators or news data, which might lead to better results. We will demonstrate this in some of the case studies, and overall we find key supervised regression and time series modeling frameworks which are used in asset class prediction are generally better performing. So thank you. We'll end it here.